Hi, welcome to the lecture series on image recognition with neural networks. My name is Long Nguyen. The goal of this lecture series is to give a widely accessible introduction to neural networks. We're going to write a Python program from scratch that recognizes handwritten digits without using any libraries or frameworks. The prerequisites are minimal. We only need some precalculus, some program experience, preferably in Python, but not necessary. But for a quick refresher, I have some links below in the description to some Jupyter notebooks that can help you review some Python. Although the prerequisites are minimal, the course will cover a very broad range of advanced topics. Here's some preview. We're going to have an introduction in this lecture. Then we'll talk about functions and their computational graphs. This is a good review for those who haven't done math for a while. Then we'll formalize the problem. And then we'll talk about some tools that we need to understand the algorithm, namely calculus. We'll talk about what is a derivative, what is a gradient. And we'll do this mostly from a geometric, intuitive point of view. Then we'll discuss the main algorithm, which is gradient descent, and talk about how backpropagation allows us to implement the algorithm. And then finally we write the entire program. And amazingly, this will only take about 50 lines of code. And then in lecture 7, which is optional, we'll go through some proofs using calculus for all of the backpropagation equations that we use. So these videos have PowerPoint slides, and then we also have some Python demo using Jupyter Notebook. All the slides, demo codes, data sets, all the homework, Jupyter Notebooks are available on my website. See the links below for in the description of the video. Okay, so how do we write a program that accepts an image as an array of pixels and classify it correctly? It seems almost impossible. I mean, to really appreciate this problem, we are hardwired to look at a picture and be able to interpret it, but the computer only have disposal to the pixel value, which is a bunch of numbers. Imagine trying to recite a list of numbers to someone and expect them to be able to identify the object of those pixel values. So this is a really hard problem. And so our objective in this lecture series is to write a Python program that recognizes handwritten digits and understand the math behind such a program. We'll be using the MNIST dataset of handwritten digits. So these are images that are 28 by 28 grayscale, the low resolution images. The pixel value from 0 to 1, white is 0 and black is 1. All those intermediate values are different shades of gray. Here's a sample of all those handwritten digits. So we first take our image, which is a 2D array, 28 pixel by 28 pixel. We're going to flatten it into a 784 by 1, which is a column vector, 784 rows, 1 column of pixel value. So for example, 1, 2, 3, 4, which is a 2D array, when you flatten it, it becomes a vector, or column vector, 1, 2, 3, 4. And so each image, after we flatten it, is a point or vector in R784. So an image, also every image has a label, a class label, a number from 0 to 9, indicating what digit it is. So the MNIST dataset encodes this label as a one-hot vector. A one-hot vector is basically a vector that has exactly one entry that is equal to 1, and every other entry is equal to 0. So in this case, because we're trying to encode 10 categories for the 10 digits, our label will be 10-dimensional. So for example, if I want to encode the digit 2, then I want the 1 to be at index 2, and then everything else to be 0. And we similarly encode the other digits using this one-hot vector. So an image in this data set is actually a tuple, x comma y, where x is the pixel values, is a column vector of pixel values living in R784, and then y is the label, the one-hot encoding label, which is a vector in R10. And then encoding label is indicate what image x is. And so in the data set, this image is actually a 2D Numpy array, which is shape 784 by 1, which is 784 rows, 1 column, and the label is 10 row by 1 column. Again, these are notation for Numpy library, and we'll talk about that in the next lecture. So let's investigate this dataset with Python. So here's a Jupyter notebook. So we're going to load up the dataset. This is where all the data is living in, and the Numpy is the library we use to do matrix multiplication, linear algebra, and we'll put it as NP, and then matplotlib. We won't talk about this too much. It just allows us to plot some pictures in a second. So we're going to run it by hitting Shift Enter, and then here's the data. We're going to load all the data, the training data, which we use to teach the computer patterns that it can help identify features from the images. And then the test data, which we'll use after the training process and see if our computer can recognize new images. And we won't use the validation data in this course. So these are actually all lists, a Python list. And so for example, what if I want to know how many images are in the training data? Well, because it's a Python list, we can use the length function. And this will tell us that the training data has 50,000 digits, or 50,000 images. Well, how do we extract those images? Well, this is a list, so we can extract it using this bracket notation, so training data. So this is the first image, it's not an index 0, but we want to remember an image is actually a image label tuple. So we have to extract the image, so we're going to extract it by using index 0, which is the first component of the two tuple. And then in the same way, we're going to extract the label. Again, this is the first image, and 1 is the second component, which is the label component of the image label tuple. Now, if I were to print out the shape of these variables, then that would tell me, so again, these are 2D NumPy array. It'll tell us the shape of these 2D arrays. So the image is 784 by 1, that's a column vector, and the label is also a column vector, which is 10 by 1. Okay, let's print out the label, see what it looks like. So we talked about how the label is one hot encoding. So here it is, everything is 0 except for 0, 1, 2, 3, 4, 5. So that means that this label represents the number 5. And so I can print out, if I like, the pixel value, but it's not going to help me see what kind of image it is, because again, most of these are zeros, and there's going to be a lot of gray and black in the middle. But this is a one long column vector, so it won't help me see what image it is. So here's a function that allows me to plot this image. So I'm going to run this. We don't have to worry about this function. It's not really part of the course. I'm just going to run that, and I'm going to call it. You're welcome to look at that code and kind of see how it does it using the matplotlib library. But so we're going to plot it by calling it and plotting the first image. So notice that this is the number 5, which agrees with the label that we saw earlier. Again, this is the label for the number 5. I can even plot a bunch of images. So if I run this function, I can call it. Here's the training data, and I want to use something called slicing. I want to start with 0, and I'm going to go up to 10, which means it'll go from 0 to 9. So this will plot the first 10 images of training data. So notice here it is. Here are the first 10 images. Okay, let's get back to the slides. So we want a function that accepts the raw pixel data, which is a vector in R784, and output the class score, which is a vector, a 10-dimensional vector. This function is called the score function, or the classifier. It allows us to see which class has the highest score, and allows us to kind of see the prediction from those scores. So a good score function should assign a high score, a score close to 1, to the correct class, and a score close to 0 to the incorrect classes. So for example, if you have an image X and we apply our classifier, our function, and the output looks like this. Notice a lot of these class scores close to 0. So that means that, for example, the first class is close to 0, and that represents the class 0. And so that means that it's probably not going to be the number 0. As I keep going, I notice that the class 3 has the highest score, a score close to 1. So for this image, the function thinks that this is a 3. And because that's the class that has the highest score. In Numpy, there's a function called argmax that takes a vector and returns the index of the largest value. So if I call argmax on this vector, it will return 3. And that will be my prediction. So we want this function that basically take x, and when you apply f of x to it, we want the function to approximate the label. And so we want the output of f of x to be approximately equal to the label, which is the true value for the image. So our model, we have classified the image correctly if the class with the highest score in the vector f of x, so we look at the vector of the prediction, the one with the highest score, if it matches up with the class with the number 1 in the label, then we say that the function has correctly classified that image. Again, f of x won't be exactly equal to the label, but it'll be close to it. And so we take the highest score as our prediction for our model f. So it seems like this function f can be very complicated. How can it extract information about images if it's a simple function? But it turns out that f is actually a composition of just 2 functions, and both of which we've seen in precalculus. So here they are. The first function is called an affine function. You simply take an input vector x, you multiply it by w, which is an m by n matrix, and then we add the vector b to it. So this is just what we see from precalculus, matrix multiplication and matrix addition. So that's the affine function. The second function is called the sigmoid, or the logistic function. It's 1 over 1 plus e to the negative x. And this function you might have seen when you did logistic regression in precalculus. The domain is the set of all real numbers, and the range is from 0 to 1. And so typically we deal with vectors, and but this function only take a real number input. So we need to extend this to vectors. So the way we do that, we do it kind of the most natural way. If we have a vector x, then sigma of x is going to be applied component-wise to each of those entries of x. So sigma of 1, 2, 3 is sigma of 1, sigma of 2, and sigma of 3. Excuse me. So we take the affine function. It turns out we take 2 of them. So f1 is going to be an affine function with w1, b1. f2 is another affine function with w2, b2. And then we also take the sigmoid function. And then it turns out that if we compose them in this way, we first apply f1, which is the affine function, and then we apply the sigmoid function to it, again applying this component-wise. Then we apply f2, which is another affine function, and then we apply the sigmoid function to it again. And so it turns out that this series of composition will, with the right choices for the parameters w1, b1, w2, b2, if we pick the right choices for those, this is the function that will correctly classify the MNIST dataset with an accuracy of 95%. So it's pretty amazing that we can do that with 2 very simple functions. So here's kind of the big picture. We're going to use a 2-layer neural network to do this. And so let's kind of look at the architecture. So again, the input x is the image, which is a vector in R784. And then we're going to apply, again, the affine function f1 and then sigmoid. And we're going to choose w1 and b1 so that it takes that vector and send it to a vector with 30 dimension. So the way we do that is we pick w1 so that w1 is 30 by 784. So that when we multiply by x and you add b1, which is 30 by 1, then you get a vector in 30 dimension. Then we do this again and apply the second affine function and then apply sigmoid again so that the output of that gives you a vector in an R10. So for that to happen, W2 has to be 10 by 30 and B2 has to be 10 by 1. So the question here is that why do we choose 2-layer? Why can't we do 3-layer or 4-layer? And where did this 30 come from? Because it seemed kind of arbitrary. And so this is all part of something called hyperparameter tuning. So in machine learning, typically there's a lot of choices that we have to make. And we usually have to kind of play around with it until we find the best choice. So in this course, because it's a basic introduction course, we're going to kind of not really talk about hyperparameter tuning. And we use this architecture and we just see how this will work with the algorithm. So this is the main network. So the function we have is this compositions of affine function and sigmoid, and we do it twice. And so this function depends on the parameters W1, W2, B1, B2. So these are called the parameters of f. So for example, a function f, the linear function f of x is mx plus b. Takes an input a real number x. So m and b are parameters of this function. If I change m or change b, then I change my function. So in the same way, our classifier depends on W1, W2, B1, B2 parameters. If I change my parameters, then I change my function. So I'm hoping to find the best parameters that will recognize my images. And so we'll denote this dependency of f on these parameters by writing f of x, and then we'll have a semicolon here. And then after the semicolon would be all the parameters that f depends on. Sometimes we'll combine the w's and the b, so to write w and b like this. So the parameters w1, w2, b1, b2, as I said, are learnable parameters, because these parameters can learn from our data, and as it analyzes the data, it learns from it and modifies itself, and so that it gets better and better at reflecting the data. So finding the optimal parameters for f becomes a calculus problem, and it's actually just an optimization problem. And so how does this function learn the best possible parameters to be able to represent or classify images? Well, it does this in the same way that we teach a child how to recognize images. We show a child a picture of the number 3, and we say, this is the number 3. In other words, we give a child a picture that is labeled. So in the same way, we're going to give the computer a lot of pictures that are labeled and hope that it can develop techniques to learn it to then identify the features of those classes. So this is a data-driven approach. This algorithm needs a huge amount of data, and all these data has to be labeled so that I can find patterns among those pictures. So this set of images that are labeled is called a training set. And as the computer looks through the training set and adjust the parameters and try to learn from data, this process we call training the classifier. And so, for example, if I were to write a program that can recognize cats and dogs and mugs and hats, then we have to give our program label pictures of those things. So I have to give it a lot of pictures of cats, a lot of pictures of dogs, etc. And so after the training process, once we obtain the best parameters, then we can use those parameters to make predictions on new images that the computer hasn't seen before. And so that set is called the testing set. And so the accuracy of our model is measured by comparing the predicted value from the model and the true values from this testing set. And the true value is sometimes called the ground truth. Okay, let's show you how this is done. So we talked about the sigmoid function, so let's implement that in Python. So we're going to return, so this is a function, and it takes in input x. We're going to return the output, which is sigmoid, 1 divided by 1 plus, so the Numpy array, which is NP, has a function called exp, which is exponential, negative x, and we're going to hit shift enter. So there's our function that we'll use later. As we mentioned in the lecture, if you have a vector x, then sigmoid, which normally take a real number, it can be applied to a vector by applying it component-wise. And so, for example, if it's 1, 2, 3, then sigma x is sigma 1, sigma 2, sigma 3. So in code, here's how I create a Numpy array, np.array. So this is a 2D array, has 3 rows and 1 column. So here's 1, 2, 3. And I'm going to apply sigmoid to this vector x. And notice I get the same vector as this. So again, this is applying sigmoid individually to each of these entries. Okay, so we know about these affine function and about the sigmoid function. We know the classifier, the form of the classifier, which is this composition. So all we need is now the parameters. And so what I do here is that I'm loading these parameters from a file, and these parameters have been trained already. So I've run the program already, and I've trained it. In fact, the training involved examining 50,000 images 30 times. And once I've trained it, then these parameters are very good parameters that can allow me to get a high accuracy model that can classify and recognize images. So let's load these parameters and see if our function can use those parameters to recognize images. So here's the classifier. It takes an image X, and then it has all these parameters. Again, we've loaded them, so we're gonna see if we can make prediction. So the way it works is that we're gonna take X and we're gonna multiply it by W1. So let's just call this Z1. Z1 is, so Numpy has a function called dot. This represents matrix multiplication. So we want to multiply W1 with X. And then we're going to add to that B1. So that's the first affine function. Then as you remember, let's call A1B. We have to call the sigmoid function on the output of the affine function, which is Z1. So sigmoid of Z1, let's call that A1. Then we do this again. We're going to call Z2 be equal to NP dot. We're going to multiply W2, the second parameter of W, with A1, which is the output of the previous step. We add to that B2. And then finally, A2 is equal to sigmoid of Z2. Then we return A2. Now let's run that. That's it. Just a bunch of matrix multiplication and addition, and applying the sigmoid to the output. And this is the function, amazingly, that can recognize images. So let's try it out. So I'm going to call the function on my training data, and I'm going to send it over the first image, but I need to send over the pixel, so I'll extract out the pixel, and I do that, and I get, oops, I'm missing the parameters. I need to give it the parameters, W1, W2. Remember, we loaded these parameters earlier. These are the ones I've trained previously. If I do that, then I get this prediction. This prediction is a vector of 10 dimension, and the highest score among these prediction would be the class that the model is predicting. So I mentioned earlier that there's a Numpy function called argmax, which returns the index of the highest score. So if I send over this vector, let's copy and paste this, then we're going to see that the index 5, so this is the one that is the, actually this is the one. So index 5 is this one. So that means that our function thinks that the image here is the number 5. And let's just make sure that's true. So let's actually plot the image now. So we had this function earlier, plot. So training data. Okay, we want the pixel value. So if I were to plot it, there it is, the number 5. So that it actually classified this correctly. Let's do another one. Let's say this is 10. So let's see what the model tells us. The model thinks that this is the number 3. So let's try it out and plot it, see what number this is. And there it is, the number 3. So this function is very accurate. It turns out that it's about 93-94% accurate. So here's another function that will make a prediction on a bunch of images. So images is a list of images. So the way it works is that we've created an empty list called prediction. For every image in this list of images, we're going to call the function f on, again, the bracket 0 means you take out the pixel of the image. So we send over the pixel with these parameters that we've loaded. And so A is the output, the prediction output. Then we find the argmax, the one with the highest score. Then we add that prediction to our prediction list. Then we return the list. So there's that function. Let's run it. And now we're going to call that function on, say, the first 10 images. So I use the slicing again, 0 to 10, the first 10 images. Again, I need those parameters. So W1, W2, B1, B2. And so those are the predictions for the first 10 images. So let's verify that by calling plot images. And again, I'm going to send over the first 10. And notice that the prediction matched up exactly with the actual images. That's pretty amazing that we can, very basic math, some matrix, some precalculus stuff, somehow can be able to give us a function that can represent or recognize images. Okay, let's go back to the slides. So the heart of this process is an algorithm called gradient descent. It's an algorithm that requires some calculus. So even if you don't know calculus, we're going to go over some intuition and some geometric definition that allows you to have an idea of what a derivative is, what a gradient is, so that we can really understand the algorithm and be able to implement it. So we'll cover those in the next few lectures. The material of these lectures come from this book, the first book. It's a free online book written by Michael Newson. It's a great book. It's where I learned machine learning for the first time. Handwritten also has a bunch of classes on Coursera that teaches about machine learning. And Stanford has a course called CS231 that has really good notes on these kind of material. And so I hope to see you in the next lecture.